Okay. All right, so it looks like we're good to go and it's time to start. So we'll go ahead and get started. Glad all of you could make it tonight. We're kind of coming up into the home stretch. We've got this week where we're going to do some two sample inferences. So we're going to be doing confidence intervals and hypothesis testing for two samples. We're going to look at sample means and we're going to look at sample proportions. And then next week, we actually have two lessons that we need to cover. We're going to be doing linear regression, and we'll also be doing the chi-square tests next week. That will finish out our meet sessions then. So we just have one more meet session after tonight. That's because as you've gotten my announcement for the week, it was emailed to you and posted to the course page over the weekend. You know that we have to encourage you to take the final exam as early as you can. The final exam is available. It was available starting November 30th, I believe. Yeah, November 30th, and is available until December 17th, which is the due date for it, the last day you can take it. The campus will be closed, will be closing on December 18th. So if you're taking it with an offsite proctor on the 17th, chances are I'm not going to get your final exam before the campus closes for the winter break. In that case, I'll just give you an incomplete for the course grade. That's all I can do. And then in January, when I get the tests uploaded to my folder, I will grade your final exam and then I'll issue a grade change form at that time. So if you can take the final exam a little earlier than the due date, you increase your chances of getting the final exam back to campus in time to get to my folder in time for me to grade. And grades are due pretty quickly after that as well. So we won't be meeting the 16th because hopefully you will have taken your final exam by then. Instead, next week I'll be sending out a review for the final exam over the last 6 weeks of the course. And I will be giving you the key for that, and I'll also record a solution video. So I'll walk you through the entire solution rather than just the answers. And that way, it would be what I would do in our final meet session. As far as going through that final exam review with you. But I'm just going to make it available much earlier since a good number of you are going to be hopefully taking it early. So Stephanie, you need to contact the testing center with that question. I submit the test to the testing center and then I have nothing to do with it. I don't touch it after that. So I don't know when it gets submitted to your proctor, but it should be submitted to your proctor already. I said to make it available starting November 30th. So it should be made available to your proctor by now, but you could check with the testing center to be sure. Any other questions before we get started? Go ahead, Amanda. Yeah, if you've been taking the test at the testing center, Amanda, you would just go there to take your final exam as well. Yeah. Yeah, we have some people in the class are from Central Ohio, and of course you're using the testing center, which is wonderful. It's very convenient for all of us. But we do have people from all over the United States who have to get the remote proctors. Just depends on where you're at. But yeah, it'll be available at the testing center, and if that's what you said where you were going to take it, if that's the proctor sheet you turned in, then they have it for you there. All right, so this week, as I said, we're working on inferences from two samples. We're going to start with the inference for the population mean when we're talking about two samples. And there are two situations where we encounter the question, is the population mean from this group the same as the population mean from that group? So we might say, you know, is the population mean blood pressure the same for men as it is for women? You know, we do that with a lot of health measurements. You know, do they differ by gender, or are they the same for the genders? And so there are two types of groupings that we have when we're testing for the population mean or when we're estimating the population mean. Sometimes we have independent samples, and sometimes we have paired or dependent samples. So let's see if we can kind of tease these out from the examples that I give. So a drug company has developed a new drug that is designed to reduce high blood pressure. The researchers wish to design a study to compare the effectiveness of the new drug to that of the old drug. Here is one way in which the study could be designed or can be designed. So here we have design one. 2 samples of individuals are chosen. One sample is given the old drug and the other sample is given the new drug. After several months, blood pressures of the members of both samples are measured. We compare the blood pressures in the first sample to the blood pressures in the second sample to determine which drug is more effective. In this design, the samples are they independent or are they paired, do you think? Now, paired is another word for dependent, and independent and dependent have the same definitions that we learned about back in chapter 4. And a lot of you are saying independent, and you're absolutely right. There are 2 samples that are totally independent of one another. They contain different individuals. What happens in one sample does not affect what happens in the other sample. So we've got the independent samples here. This means that the observations in one sample do not influence the observations in the other. But here's another way that we could set up this study. In design 2, we take a single group of individuals. They are given the old drug, for a whole month. Then their blood pressures are measured and recorded. Then they switch to the new drug for a whole month, after which their blood pressures are measured again and recorded. This produces 2 samples of measurements, the first one from the old drug and the second one from the new drug. We compare the blood pressures in the first sample to the blood pressures in the second sample to determine which drug is more effective. So in this design, the samples are what? Paired or independent? They're dependent or paired, that's right. Dependent is another name for, I put them both down here because sometimes we use those interchangeably. Dependent. So each observation in one sample can be paired with an observation in the second because we're using the same individuals to take both of those drugs. So when we go to form a confidence interval or do a hypothesis test, we have one process for independent samples. We have a different process for paired samples. So that's why it's important to be able to distinguish what type of samples you're working with right from the very start. So the first thing we're going to look at tonight is the hypothesis test for the difference of 2 means from independent samples. 2 samples who, you know, the observations of one sample does not affect the observations of the other sample. So this method requires the following assumptions. We have simple random samples from the 2 populations that we're comparing. The samples are independent of one another, meaning that one sample does not influence the other in any way. And each sample size is large and greater than 30, or the population is approximately normal. So essentially, they're the very same assumptions that we had back in chapter 7 and again in chapter 8. The only exception is number 2. We've got 2 samples and the samples are independent. So we're going to do the p-value approach here. So scores on the National Assessment of Education Progress, NAEP, mathematics test range from 0 to 500. In a recent year, the sample mean score for its students using a computer was 309, with a sample standard deviation of 29. For students not using a computer, the sample mean was 303, with a sample standard deviation of 32. Assume there are 60 randomly selected students in the computer sample and 40 randomly selected students in the sample that didn't use a computer. We can see that the sample mean scores differ by 6 points. 309 minus 303 is where we're getting the 6 points from. So the students using the computer, their mean was 6 points higher than those who were not using the computer. Now we're interested in the difference between the populations, that's 6 points, which will not be exactly the same as the difference between the sample means. Is it plausible that the difference between the population means could be 0? How strong is the evidence that the population mean scores are different? So the first thing that we're going to do is we're going to check our assumptions. So number 1, we have 2 simple random samples. Assumption number 2 says the samples are independent. And we can say yes to that. We have 60, sorry about that. There we go. We have 60 in one sample and we have 40 students in the other sample. They're not the same, so they're totally independent of one another. And 3, we have large samples. My first sample, n sub 1, is equal to 60. That's greater than 30. My second sample, n sub 2, is equal to 40, which is also considered large because it's greater than 30. So we could check that one off as well. So when we set up the hypotheses, they're going to be a little different than we did back in chapter 8. They're, I think, maybe in some ways a little easier. Our null hypothesis will always look like this when we have 2 independent samples. The null hypothesis says that the mean from the first population is equal to the mean from the second population. And in other words, what this is saying is that the difference between the 2 population means could be 0. The alternative hypothesis, in this case, we're wondering how strong, it says, how strong is the evidence that the population mean scores are different? So we're going to write that as the mean population mean from the first population is different than the population mean for the second population. So notice that we have subscripts on our parameters now, mu sub 1 and mu sub 2. We don't have any numbers like we did before in the hypotheses. We don't have mu equals 70, mu does not equal 70. That's what we would have seen with the 1 sample hypothesis test that we did last week. This week we have 2 samples, 2 unknown parameters, and we use both of those parameters in both of the hypotheses that we write. So this would be a 2-tailed test, just like it was last week, because of the not equal to sign right here. And we're going to see that the process is essentially the same as it was last week. So we have different notation in some of the steps, and we of course have a different calculator function that we're going to be working with. But the process itself is identical. The 5 steps are identical to what we did last week. So we need to find the test statistic and the p-value. So the way we're going to do that, and I've got the calculator screen showing for you, so hopefully you've got your calculators handy and you can start pushing some calculator keys with me and know that everything you need to know is in your notes here. So we're going to go to stat, we're going to go over to tests, and we want to find the 2 sample t-test. Now, can anyone tell me why I need the 2 sample t-test here? What tells us I need a t-test? Yeah, sigma's unknown. Good. That's right, Amanda. It's because sigma's unknown. 2 sample tests could be a z-test or a t-test. It all depends on what's given. So if we look back at our problem, we have a sample standard deviation of 29, and we have another sample standard deviation of 32. And because these are sample standard deviations, they're not population standard deviations, that right there tells us this is going to be a t-test. If those had been values for sigma, then we would have had the 2 sample z-test. But we've got the 2 sample t-test because we were given sample standard deviations. So we're going to come down here to number 4, 2 sample t-test. And you'll notice that the screen looks very similar to the t-test that we did last week. We've got stats to put in, so I'm going to do the stats mode. So it needs our sample mean and our sample standard deviation. It's just that there are 2 sets of the input. So the sample mean, the sample standard deviation, and the sample size for the first population. That's our X bar 1, SX1, and N1. Then we need the sample mean, the sample standard deviation, and the sample size for our second population. That's X bar 2 sub 2, SX sub 2, and N sub 2. So looking at the problem, the sample mean for our first sample is 309. The sample standard deviation of that first sample was 29. Oops, sorry. Yep, that's right. And the sample size, we had 60 students. For our second sample, the first sample were the students who used the computer to take the test. For the second sample, those students who did not use a computer to take the test, their sample mean was 303. Their sample standard deviation was 32, and we had 40 in that sample who did not use the computer. So we just have a little more input, but it's the very same input that we had last week. So now we come down to which type of test do we have, the two-tailed, the left-tailed, or the right-tailed. And as I said earlier, this is a two-tailed test. mu1 does not equal mu2. And now we've got the pooled question. We are always going to leave the pooled question no. We're not going to change that to yes. The question about pooling the data is actually about pooling the standard deviations to when we calculate the test statistic. And so if the standard deviations are very similar, we might want to pool our data. We're not going to discuss that particular technique in this course. It's a rare technique. So this pooled question, we're not going to talk much about it. It's always going to be no. We're not going to assume that the standard deviations are so similar that these two samples came from the same population. So let me just get this out of here. Let me get back to where I was. Okay, here we go. So we're going to leave that as no, and now we're ready to calculate. So our test statistic, can anyone tell me what the test statistic is, rounded to 3 places? Good, 0.953. It's the t-score that we see. What about the p-value, rounded to 3 places? 0.343. You'll notice that we're given the degrees of freedom. That's going to be helpful in a little while. When we have 2 samples, there are a couple of ways to determine the degrees of freedom. You'll read in your textbook that the shortcut method for determining the degrees of freedom is to take the smaller of n sub 1 minus 1 and n sub 2 minus 1. So in this case, that would be 39. We'd have n sub 1 minus 1, 60 minus 1 is 59, n sub 2 minus 1 would be 40 minus 1, 39. So the shortcut method says our degrees of freedom is 39. The smaller of the 2 degrees of freedom for the 2 samples. There's a more complicated formula that gives us more accuracy, and the calculator has that programmed into it. So using the more calculated program, our degrees of freedom is about 78, 77.95. That will come in handy if we need to a critical value. Then, of course, it's just going to give us the input, what we put into the calculator for the statistics. So there you'll see displayed what we entered in our screen. So we've got those screens on our notes here. So hopefully that will be a good example for you. So our test statistic T, we said was 0.953. And our p-value is 0.343. And of course, we're going to compare that to alpha. We're going to use 0.05 for alpha. So we know that this is much bigger than 0.050, which is equal to alpha. So what will the decision of our test be? Are we going to reject the null hypothesis or fail to reject the null hypothesis? Yeah, do not reject the null hypothesis. Awesome. And we need to justify it. So why do we not reject the null hypothesis? Yeah, the p-value is greater than alpha. And now we need to state the conclusion of the test. So we can say there is not enough evidence to conclude that the population means are different. All right, so any questions about that so far? Okay, Rachel's good. All right. Okay. All right. If there are questions, just to pop them in the chat box there. It's good. So now we're going to take a look at the critical value approach. Just like in last week's Connect Math homework, I think you're going to have some homework problems that ask you to find critical values again. So we'll take it and do one of those so you have an example of that to fall back on. When it comes to testing on the final exam, you are not told how you have to perform the test. So you can use the p-value method, you can use the critical value approach, whichever one you want on the final exam. But of course, I want to make sure that we cover as many of the bases as we possibly can for the homework. So let's take a look at the critical value approach for two samples. So treatment of wastewater is important to reduce the concentration of undesirable pollutants. One such substance is benzene, which is used in an industrial solvent. Two methods of water treatment are being compared. Treatment 1 is applied to 5 randomly selected specimens of wastewater, and treatment 2 is applied to 7 randomly selected specimens. The benzene concentration in units of milligrams per liter for each specimen are given as follows. We're going to assume that the concentrations have an approximately normal distribution. That's because our sample sizes are small. So we have to be able to assume that. How strong is the evidence that the mean concentration is less for treatment 2 than for treatment 1? We will be testing at the alpha equal 0.05 level of significance. So the first thing we're going to check, of course, is our assumptions. So the first assumption is we have 2 simple random samples. We can check that. 2 is that the samples are independent. We can check that off. And 3, the samples are large, meaning greater than 30. And of course, we have to say no to that. Or the populations are approximately normal. And we were told that the populations were approximately normal, so we can check off that part of the assumption. So we've met all 3 assumptions on that. So how about the hypotheses? The null hypothesis, what do you think that's going to be? Does zero play a role in the conclusion? No, zero is going to play a big role in our confidence interval. But zero, as far as the conclusion goes, the difference equaling zero is what the null hypothesis says. And then the alternative says the difference does not equal zero. It's either greater than zero, less than zero, or different than zero. And ours said different than zero. But the number zero will play a very important role when we get to confidence intervals for these differences. So how am I going to set up my null hypothesis? Look at the last example. The null hypothesis is going to be exactly the same for every single one of these independent tests. Yep, mu1 equals mu2. Awesome. Mu sub 1 equals mu sub 2. And again, this means no difference, or the difference is equal to 0. What will my alternative hypothesis be then? We are, let me see. How strong is the evidence that the mean concentration is less for treatment 2 than for treatment 1? Other way around. Yeah, mu sub 1 is greater than mu sub 2. Yeah, so we have to be careful when we set up the alternative hypotheses. How strong is the evidence that the mean concentration for treatment 2 is, the mean concentration is less for treatment 2, so the sign needs to be pointing to mu sub 2 than for treatment 1. But treatment 1 comes first, mu sub 1. So if mu sub 2 is less than mu sub 1, mu sub 1 has to be greater than mu sub 2. And we write it in the mu sub 1, mu sub 2 order. So we can't see less than and automatically write down the less than sign. So you have to, it's going to be careful reading in these problems still. So make sure you read that question carefully, because you're going to get this flip-flopped every once in a while in the homework and, you know, possibly on the test. So just make sure you read it carefully here. So it's saying use of, sometimes what I do is I write it out. How strong is the evidence that the mean concentration is less for treatment 2 than it is for treatment 1? So that's what the problem says. We just have to flip that order, because in our hypotheses, mu sub 1 always comes first. And so if I put mu sub 1 first, that less than sign changes to a greater than sign for mu sub 2. All right, so there's our hypotheses. Now, of course, we can go ahead and on your calculator, you don't need my help with this really. You'll need to put your treatment 1 in L1, put your treatment 2 in L2, and then go to over to Stat, Calc, and go to the 2-sample t-test number 4, but this time choose data. And that'll be a much shorter screen. You just have to tell it where the data is, set up your alternative hypotheses, say no to the pooled question, and calculate. So go ahead and do that and tell me what you get for your test statistic T and your p-value. Good. So our t-value, our test statistic is 1.590. Awesome. And our p-value is 0.07. And what does it round to? 272. Yep. Perfect. So this is what you should see when you do exactly what I told you to do. After you enter the treatment 1 into L1 and treatment 2 into L2, you would go to tests, pick up number 4, 2-sample t-test, change it to data. When you change it to data, you're going to see where's your treatment, your first treatment, you put that in L1. Where's the second treatment in L2? Leave the frequencies as 1 for both of those. Choose your sign here, which is going to be the greater than symbol right here. U1 is greater than mu2. Say no to the pooled data and then calculate. So when I came into this screen, it was still, I hadn't set the screen up in the second one. The second one is the setup screen for this problem. And it was carrying that mu1 does not equal mu2 from the first problem that we did. So that's what you would have had to change it to. And so here is our test statistic. And of course, here is our p-value right here. So if we're going to do the p-value is different, if your p-value is different, you probably have, this is where your problem is going to be most likely. If your p-value is different and everything else is the same, you didn't choose the correct test. Each of those tests will give you a unique p-value. So if you check that EVA, I bet you that's where you're going to find your mistake. Yep, that's where it is. So yeah, you have to make sure that you choose the right test. This is a right tail test. So yeah, a left tail test, and you're going to have 0.929 for that, I think, 929 or something like that, 928 maybe. And if it's a two-tailed test, then you're going to have 0.15 something, 0.14 something, 0.15 something. Yeah, because it figures the p-values differently for each test. All right, and that's another thing to check on Connect Math. If you're getting one of the values wrong and the other's right, make sure you check the alternative hypothesis, the type of test that you put in. That can cause some problems. So we're going to calculate the critical value for this particular test. And we can either use the table like we learned last week. I'm going to go ahead and use the calculator here. If we're using the calculator, we're going to see that we have inverse t. Inverse t, we have to give it the left area. So if this is a right tail test, if you look at it right here, this is a right tail test, and we have 0.05 in our critical region because alpha is equal to 0.05. What is the left area for my critical value? It's going to be 0.95, right? 1 minus 0.05 gives us 0.95. So 0.95 is my critical, is my left area. Now, my degrees of freedom, that's where I said this is going to come in handy. When you're finding your critical value, look at what the calculator gives you as your degrees of freedom. It gives us 9.7 as our degrees of freedom. So we're going to use our degrees of freedom that the calculator gave us to get the most accurate critical value. So when I put that on my calculator, so second VAERS, I'm going to come down here to number 4, inverse t. 0.95 is my left area, and 9.7, my degrees of freedom. So it's going to give me a critical value of 1.818. And I'm just going to get that from my calculator. So my critical value is 1.818. My test statistic is 1.59. That's going to come in here somewhere. So what would the decision of my test be? Reject or do not reject? Okay, so you reject. Why would we reject it? Because we have to justify. So yeah, and if it's not in the critical region, then we are not going to reject it. Yeah, so this is a do not reject the null hypothesis because our test statistic is not in the critical region. So our critical region begins at 1.818. Our test statistic is less than that, 1.59, so it doesn't make it into the critical region. So this line right here, when we do the critical value method, what we do is we set up a line right here at 1.818. And what we're saying is if our test statistic crosses that line, the difference is so big, it's too big to have happened by chance. So we're going to have to reject the null hypothesis. If the statistic doesn't cross the line, we have a difference, but the difference is not a big difference. It's not statistically significant. That kind of a difference could have happened by chance, just by the chance selection of the specimens that were in our simple random samples. So when we talk about statistically significant, what we're saying is that the difference that we see from what we're expecting is so different that it could not have happened by the chance of the samples that we selected right there. So the conclusion of our test then is something like this. There is not enough evidence to conclude that the mean concentration for treatment 2 is less than the mean concentration for treatment 1. Yeah, that works with the negative side also, Stephanie, but it'll be in reverse. So if our test statistic is closer to 0 than our critical value, that's a do not reject. If the test statistic is further away from 0 than the critical value, then that would be a reject. So it works the same for the left tail test and also the same for the two-tail test. So if the test statistic is in the tail, reject. If the test statistic is not in the tail, do not reject, no matter where that tail is. Yeah, and that will always work for you. All right, good questions and good feedback and participation here. So we, I think we're gonna do one more for, oh, we're gonna take a look at the confidence intervals next. Okay, so looking at confidence intervals, our example is this. A drug company has developed a new drug that is designed to reduce high blood pressure. To test the drug, a sample of 15 randomly selected patients is recruited to take the drug. Their systolic blood pressures are reduced by an average of 28.3 millimeters with a standard deviation of 12.0 millimeters. In addition, another sample of 20 randomly selected patients take the standard drug. The blood pressures in this group are reduced by an average of 17.1 millimeters with a standard deviation of 9.0 millimeters. Assume the blood pressure reductions are approximately normally distributed. Find a 95% confidence interval for the difference between the population mean reduction for the new drug and that of the standard drug. So the confidence interval is for the difference between the population means. So this is where I said 0 was going to be an important number. So we're going to check the assumptions. The assumptions are the same as they are for the hypothesis test. First, we have 2 simple random samples. We know that the samples are independent. They're different people in each of the samples. And the third thing is either that our samples are large, meaning greater than 30, of course, which they are not. We have 15 in one sample and 20 in another sample. Or we know that the populations are approximately normal. And we're told that we can assume that the populations here are approximately normal, that the blood pressures reductions are approximately normal. So we've met all 3 assumptions. So to calculate the 95% confidence interval, we're going to go over to STAT, we're going to go over to tests, and we're going to come down to the 2-SAMP T interval. So 2-SAMP T interval is going to be number 0 in our list. And we have statistics here. So for our first sample, it looks like the sample mean is 28.3. Our sample standard deviation is 12, and we had 15 in that sample. For our second sample, the mean was 17.1. Standard deviation was 9, and we had 20 in that sample. The confidence level that we want is 95%, so 0.95 is good. We always answer no to the pooled data, and now we're ready to calculate. And so you'll notice that the confidence interval that it gives us, 3.59 1 to 18.809, the confidence interval is not really centered around our means. One of the means was 28, the other one was 17, so one mean is in there, but the other mean is not. This is the confidence interval for the difference between those 2 means. So the difference between the 2 sample means was what, about 11.2? So it's centered around 11.2, the difference between those 2 sample means, not around either of the means. So our interval, 3.591 to 18.809 is our interval. We can see it right here. The way we interpret that interval, we want to note whether 0 is in the interval or not. So if we look at our interval, the interval does not contain 0. So we are 95% confident that the difference is not 0. I'm going to write that in a couple of ways here. Sorry. In other words, we are 95% confident that mu1 is greater than mu2. So we're 95% confident that the mean blood pressure for the new drug is higher than the mean blood pressure for the standard drug. Why do I say that mu1 has to be greater than mu2? What is telling me that? The difference that I'm finding here, my confidence interval, is for mu sub 1 minus mu sub 2. That's what difference between the population means. That's how we think of it. So all of the plausible differences, are they positive or negative numbers? Looking at my confidence interval. They're positive, right? So I'm 95% confident that mu sub 1 minus mu sub 2 is greater than 0. And if that's the case, then mu sub 1 has to be bigger than mu sub 2. Otherwise, the difference wouldn't be positive. The difference would be negative. So that's why I can say that mu sub 1 is greater than mu sub 2, because all of these plausible differences are positive. So we're going to kind of predict the decision for the hypothesis test, mu sub 1 equals mu sub 2 versus mu sub 1 does not equal mu sub 2. So what do you think? Are we going to reject the null hypothesis, or are we going to fail to reject the null hypothesis? So what we're looking for, the difference is 0, the difference is not 0, and we've got all the plausible differences right here in my confidence interval. So what are you going to predict for the conclusion of this hypothesis test? Reject or fail to reject the null hypothesis? Yeah, we're going to reject that null hypothesis. Good. Because we just found out that mu sub 1 minus mu sub 2 does not equal 0. That means that mu sub 1 does not equal mu sub 2. And so that's going to be a reject. So if we find the p-value, we can go ahead and do that quite easily. If I go to stat tests and choose number 4, when you go to stat mode, you should see these data values recorded for you already. The computer keeps what we record, or the calculator keeps what we record. So you can come right down here to calculate, and sure enough, our p-value is 0.006, and our test statistic is 0.3031. Which of course would be a reject the null hypothesis, because our p-value is less than any alpha that we would give it. And so we would conclude there is enough evidence to conclude that the population mean reductions in blood pressure are not equal. So there's an example of our confidence interval, and it's all about whether or not the interval contains 0. So if the confidence interval contains 0, then the means could be the same. If the confidence interval does not contain 0, then the means are not the same. So 0 is a real important number when it comes to interpreting the confidence intervals. So the next thing that we're going to do is we're going to take a look at an example from for testing proportions. Then we're going to come back and look at the dependent samples for our sample mean. So we're going to take a look at inferences about two population proportions. So the method requires the following assumptions, and you're going to recognize these assumptions from Chapter 7 and from Chapter 8 with just a few alterations. First, there are two simple random samples that are independent of one another rather than just one simple random sample or one random sample. Each population is at least 20 times as large as the sample that was drawn from it. The individuals in each sample are divided into two categories, and both samples contain at least 10 individuals in each category. So they're the very same assumptions that we had for the one sample back in Chapter 7 and Chapter 8, just applied to the two samples that we have here. So we're going to take a look at the p-value approach for the testing population proportions from two populations. So in the year 2002, the General Social Survey asked 1,343 employed people between the ages of 18 and 50 whether they used a computer in their work, and 916 said they did. In the year 2008, they asked the same question of an independent sample of 615 employed people, and 465 said they used a computer at work. Assume these are two random samples from the population of employed people. Can you conclude that the proportion of people who used a computer at work was greater in 2008 than in 2002? And we're going to use a level of significance alpha equal to 0.05. So again, we're going to look at assumptions first. So our first assumption is that we have two simple random samples, and we do. The second assumption is that each population is at least 20 times larger than the sample drawn from it. So our first sample was 1,343. So we can assume that there was more than 25,000 working adults back in 2002. So that would be okay for our first population. And in 2008, we asked 615 people. So we can assume that there were more than 13,000 employed people during 2008. I just did kind of roughly 20 times 615 and 20 times 1,343. So yeah, we've got millions of people working. So we've definitely met assumption number 2. Number 3 says that there are two categories in each sample. And each sample has some people who work on the computer at work and some people who don't need to work on the computer at work. And now we have the fourth assumption, which there are at least 10 in each category. So in our first sample, 916 said they did work on the computer. So 916 is bigger than 10. And so if 916 worked on the computer, 1,343 minus 916, the rest of them did not work on a computer, that's 427. So both of those numbers are larger than 10. In 2008, 465 said that they did work on a computer, that's bigger than 10. And we asked 615 people. So 615 minus 465 will tell us how many people did not work on a computer at work, and it was 150. And that is also bigger than 10. So there is more than 10 in each of the categories in the two samples. So now we're going to develop the null and alternative hypotheses. And again, it's going to be pretty straightforward. The null hypothesis says that the proportion in the first population is equal to the proportion in the second population. So it's very similar to the independent samples when we're testing two means. Instead of mu though, we use p. So instead of mu sub 1 equals mu sub 2, we're going to say p sub 1 equals p sub 2, because now we're testing for proportions. In this particular problem, we were told to assume that let me see, can we conclude that the proportion of people who used their computer at work was greater in 2008 than in 2002? Well, p sub 1 is my 2002 population. P sub 2 is my 2008. So if that's true, can we conclude that the proportion of people who used a computer at work was greater in 2002 than in 2001? So that's what my question says. P sub 2 is greater than P sub 1. So in my alternate hypothesis, I have to put P sub 1 first. So it's going to be P sub 1 is less than P sub 2 to state that correctly. So again, we've got to read the question that we're answering here very, very carefully. A lot of times the symbol is flipped on us. You just can't say was greater and write the greater than sign when you read it. You have to see what is greater than what. And a lot of times it's the reverse of the way the data is given. So we're going to compute the test statistic, and we're going to find its location in the diagram. What kind of test do we have, by the way? Left-tailed, right-tailed, or two-tailed? Yeah, this is a left tail test. So we know that our p-value is going to be a left tail of this curve right here. That's what our p-value is going to look like. So we're going to have to find the test statistic in order to find that p-value. So to get the test statistic actually and the p-value, we're going to go to stat, we're going to arrow over to tests, and we're going to come down to the 2-prop z-test, number 6, 2-prop z-test. Okay, that's fine, Stephanie. So our first sample, we had what, 916 for X1. No, did we? Yeah, 916 said that they did use the computer. N1 is going to be 1,343. Our X2, the problem says 465 said that they used a computer at work in our second sample, but our sample size was 615. And we said this was a left-tailed test, so we have to choose option 2 here. Notice that we don't have the question about pooling when we're talking about proportions, only when we're talking about means. And now we're going to get ready to calculate. And so our test statistic is a negative 3.336. And our p-value is 4.26 times 10 to the negative 4th. So our test statistic, which is a z-score, is a negative 3.336. So here's my test statistic. And the tail area of my test statistic, which is my p-value, that's 4.256 times 10 to the negative 4th. So that's going to be 0.0004256. So this is 0.0004 for my p-value. So we're comparing it, we're using alpha equal 0.05. So what is my decision going to be? Am I going to reject or do not reject? Yeah, I'm going to reject this one. Reject the null hypothesis because why? Yeah, p-value is less than alpha, which is 0.05. And now we need to interpret the decision. So For rejecting, there is enough evidence to conclude that the proportion of workers using the computer at work is greater in 2008 than in 2002. And also, Rachel would be correct as well. That test statistic would be in the critical region. If we were to find the critical value for this test, it's going to be negative 1.645. And so our critical value, I'm just going to do that in a different color, would be out here somewhere. That's going to be our critical value, and negative 3.336 is to the left of that. So we can see that our critical region right here is this red tail. Yeah, our test statistic is in the critical region. That would be another reason for it that would be right. And the p-value is low would be another explanation. So both Eva and Rachel are correct in their example or in their justification there. So we're going to do a little prediction. Will the 95% confidence interval contain 0? Type Y if you think it will, meaning yes. Type N if you think it won't, meaning no. Look at our conclusion or our decision. We rejected the null hypothesis. So should our confidence interval contain 0 in it? And Rachel's saying no. What about some other votes here? Okay, Amanda's saying no. Eva is a question. She's not sure. What about the other 6 of you? Okay, Dakisha also has a question. We're down to 5 of you. Okay, Tisha has a question. Now I'm down to 4. If I get no answer, I wonder if you're actually here or if you've just turned on the computer and walked away. So everyone can give me a yes, no, or question mark. So, Stephanie's here. Okay. She's in a question mark, so we're down to 3. Okay, I'm going to assume that those 3 have stepped away from the computer because they haven't answered. So if we take a look, we rejected the null hypothesis. Remember, our null hypothesis says that P sub 1 is equal to P sub 2. So the null hypothesis says that the difference between P sub 1 and P sub 2 is equal to 0, but we rejected that. So the interval should not contain 0. All of you are right, because we rejected that P sub 1 was equal to P sub 2. In other words, P sub 1 minus P sub 2 equals 0. That's another way to state that relationship. We rejected that 0 was a plausible value for the difference. So we're going to check that with the 95% confidence interval. So we're going to go over to stat. We're going to go over to tests. This time we're looking for the 2-prop Z interval. So we're going to come down here to option number B, letter B, option B, 2-prop Z interval. We're going to find that all of our values are in there. We're going to do the 95% confidence interval, so that's already set. And when we calculate, Sure enough, we start at a negative 0.116, and we go up to a negative 0.032 if we're going to round to 3 places. Does not contain 0. So we are 95% confident that the proportions are not the same, and our hypothesis test confirmed that. We rejected the null hypothesis, which says that the population proportions are the same. So good work there, Rachel and Amanda and Rachel, I believe, for the ones who said no. Awesome work there. Good. So the confidence interval estimate, we're going to do another confidence interval here. So in a study of the effect of air pollution on lung function, a random sample of 50 children living in a community with a high level of ozone pollution had their lung capacities measured, and 14 of them had lung capacities that were below normal for their size. A second random sample of 80 children was drawn from a community with a low level of ozone pollution, and 12 of them had lung capacities which were below normal for their size. We're going to construct a 95% confidence interval for the difference between the proportion of children with diminished lung capacity between the two communities. So we just did a confidence interval. So I'm going to let you do this one on your own. The assumptions are met. We have 2 simple random samples. The population of children is at least 20 times the sample size. There are 2 categories in each sample. Either their lungs are normal size or their lung capacity is below normal for their size. And there are at least 10 in each category. So we had 14 below normal in our first sample, and it looks like there are 36 that have normal capacity. In our second sample, 12 were below normal, so that's at least 10, and 68 were normal. So we have at least 10 in each category. So go ahead and find the confidence interval estimate for the difference in these proportions. Yeah, good work, Rachel. So negative 0.017 to 0.277. Awesome. Yep, you used option B just like we did before, 2 prop Z interval, and put in your values. I'm showing you those here from the problem. And then when you press calculate, this is going to be the interval the calculator gives you rounded to 3 places. So does our interval, okay, sure, Keisha. So does our interval contain 0? Yeah, this is a little different than some of the other intervals that we looked at. This interval begins at a negative number and ends at a positive number. So yeah, 0 is in there because 0 is where numbers change from being negative to becoming positive or vice versa. So the interval contains 0. So when we interpret it, we say we are 95% confident that the difference between the 2 population proportions is 0. In other words, we're 95% confident that the proportion of below normal lung capacity is the same in high ozone areas as it is in low ozone areas. Those are the two populations that we were looking at. So we're 95% confident that the proportions for low lung capacity or below normal lung capacity is the same. Doesn't seem to be a difference with the levels of ozone. All right, so that takes care of the confidence interval and the hypothesis test for the population proportions. Now we're going to take a look at paired samples. So we're going to use the critical value approach. So we have a sample of 8 automobiles, and we run them to determine their mileage in miles per gallon. Then we give each car a tune-up, and we run them again and measure the mileage a second time. So you'll notice in my chart here that I have 2 values for each of 8 different cars. The first value is the before tune-up mileage. The second value is the, the first value is the after tune-up mileage. And the second value is the before tune-up mileage. So the sample mean mileage was higher after the tune-up. Assume that the mileages are approximately normally distributed because we have a small sample. We only have 8. We would like to determine how strong the evidence is that the population mean mileage is higher after the tune-up. So what we have here is we have a paired sample, and these pairs are called matched pairs. By computing the difference between the values in each matched pair, we can construct a sample of differences. So this last line right here, we have a single sample of their differences. So let's see where those numbers came from. So I'm going to go to my calculator, and I'm going to go to stats. I'm going to put the after tune-up mileage in list 1 and the before tune-up mileage in list 2. So what I'm going to do is I'm just going to copy, let's see, I'm going to copy the first row into L1 and the second row into L2. So, oops, let me get this up here. Oh, good. I'll email Doug afterwards. Okay, so there are the numbers in each list. I'm going to come over here to list 3. I could clear it out, although I don't really need to, but I'm going to come up here to list 3. I want to show you something here. In list 3, I'm going to tell it to take the value in L1 minus the value in L2. So when I'm up here on the list name, notice I've got this line down here, L3 equals blank. I'm going to type second 1 minus second 2. I'm going to hit enter. And you'll notice that all of these values in list 3 are the numbers that I see in the highlighted row of differences here. 1.68, 0.87, 1.52, 0.67, 1.56, 1.33, and so on, 1.88 and 1.14. So I could take the differences by hand if I want, or I can get the calculator to take the differences for me. So this went into L1, this went into L2, and in L3, I said L1 minus L2, and it gave me those values right there. So we're going to be using list 3 here in a minute. So a little bit of an explanation as to how we're going to set this up. If we denote the population mean mileage before tune-up by mu sub 1, and the population mean mileage after tune-up by mu sub 2, then we are interested in the difference, mu sub 1 minus mu sub 2. Because these are paired samples, the population mean difference, mu sub d, is the same as mu sub 1 minus mu sub 2. Therefore, performing a hypothesis test on mu sub d is the same as performing a hypothesis test on the difference of the population means, mu sub 1 minus mu sub 2. So we're going to use the following notation. D bar is the sample mean of differences between the values in the matched pairs. So if I took the sample mean for list 3, the sample mean for list 3, that's what we're calling D bar. S sub d is a sample standard deviation of the differences between the two values in matched pairs. So our Sx, if we did the one var stats for list 3, that's what we're calling S sub d. And mu sub d is the population mean difference for all of the matched pairs. So the method for testing a hypothesis about mu sub d is the usual method for testing a hypothesis about a population mean. It requires the following assumptions, which are very similar to what we've already looked at. We have a simple random sample of matched pairs. That's the only difference here. And either the sample size is large and is greater than 30, or the differences between items in the matched pairs show no evidence of strong skewness and no outliers. In other words, the differences are approximately normal. This is required to be sure that the sample mean difference will be approximately normally distributed. So here are the steps. We're going to develop the hypotheses. Now, when we develop the hypotheses, we're going to go back to the one sample test. So remember this mu sub 1 minus mu equals mu sub 2. That's our normal hypothesis if we have independent samples. That's the same as saying mu sub 1 minus mu sub 2 is equal to 0. But we just said that mu sub 1 minus mu sub 2, we're calling that mu sub d equals 0. So here is our null hypothesis. U sub d equals 0. So remember right up here we said mu sub 1 minus mu sub d is the same as mu sub 1 minus mu sub 2 is the same as mu sub d. That's what I'm referring to right there when I wrote this down. So the question says, is there evidence that the mileage is higher after the tune-up? So this is going to be mu sub 1 is after tune-up. I'm just going to put an A for after tune-up. Mu sub 2 is before tune-up. Because remember up here, we put the after tune-up in L1, we put before tune-up in L2. So mu sub 1 is the mean mileage after the tune-up for all cars. Mu sub 2 is the mean mileage before tune-up for all cars. So that's the same as mu sub A minus mu sub B. And that's, so if it's greater, the mileage after the tune-up is greater than the mileage before the tune-up, that difference is going to have to be greater than 0. So mu sub d is greater than 0 for our alternative hypothesis, because our question said, how strong is the evidence that the population mean mileage is higher after the tune-up? So our after tune-up mu sub 1 is higher than before tune-up mu sub 2. So the difference is greater than 0. So what we're going to do is we're just going to run a t-test on this. So we're going to come to stat, we're going to go over to tests, and we're going to choose t-test for this one. We have data. What value am I going to put in here for mu sub 0? What is the value in my null hypothesis? Good, it's 0. My data is in list 3. That's where I put my differences. My frequency is 1, and of course this is a right-tailed test, so I'm going to choose option 3 here. And when I calculate, my test statistic is 9.143. And what is my p-value in standard notation? There we go. Yeah, 0.00002 or 0.00001925. Awesome. Good. So my test statistic is 9.143. My p-value is 0.00002. And I got these from doing stat, test, number 2, t-test, using data input with my data in L3. So there are the instructions for how I got these values. So my test statistic T is way out here, 9.143, and that p-value is a really, really tiny tail, 0.00002. So that's what it would look like. So what is my decision for this test? Reject or fail to reject? Yeah, this is a real strong reject, actually, because our p-value, which is essentially 0, is a lot less than any alpha we could choose. We'll use alpha equal 0.05 unless it was given otherwise. So any value that we're going to be given is going to be bigger than 0.00002. So no, that's going to be a reject. So interpreting it, we use the same interpretation that we did before. There is enough evidence to conclude that the mean mileage after tune-up is greater. So the confidence interval estimate for mu sub 1 minus mu sub 2, when we have paired samples, we're going to use the t-interval with the data that is in L3, because remember, it's the confidence interval is for the mileage difference before and after the tune-up. So we're going to construct and interpret the 93% confidence interval for the mean mileage, for the mileage difference before and after a tune-up. So I'm just going to use stat, test, number 8, t-interval, and I'm going to choose the data option, and my data is in L3. So stat, over to tests, number 8, t-interval, I have data. My data is in L3. My frequency is 1. My level of confidence is 0.93. And now I'm ready to calculate. And so my interval is 0.924 to 1.488. Does it contain 0? No, does not contain 0. Good. And that's what we were expecting. We rejected the null hypothesis where the mean is equal to 0, the mean difference is equal to 0. And so since we rejected that, we were expecting that it would not contain 0. So when we interpret it, we would say we are 93% confident that the mean difference in mileage after a tune-up is positive, because all of these plausible values are positive numbers. So, in other words, we're 93% confident that mileage after a tune-up is higher than it was before the tune-up. So when we have a paired sample, when we have paired samples, we have paired data, what happens is that the 2-sample problem is reduced to a 1-sample problem. And we use the t-test and the t-interval that we learned about in chapter 7 and chapter 8. And we do that with the differences, which are going to be in your list 3 when you set up these problems. So our next steps: listen to the interactive lecture for Module 10. If you've not done so already, that's due by end of day Thursday. Make sure that you complete the Connect Math practice homework for week 10. Complete the Connect Math homework quiz for week 10. And also complete the application assignment for week 10. So it's just a normal week this week. For our office hours next week, if you have an older calculator that does not contain this chi-square GOF, goodness of fit test that you see that I've highlighted, go to stat, go over to tests, go down to option D. If that's missing from your calculator, then you'll need to enter a program on your calculator in order to handle that for our material for next week. And there's a YouTube that shows you exactly how to do that. I've given you that link in your notes. And I've given you the program here. If you're tech savvy, you probably don't need the YouTube video to help you with that. But if you're not tech savvy, the YouTube video tells you exactly how to do that. So that's just a check ahead for next week. So when we get to that goodness of fit test, you have everything that you need on your calculator if you have an older one. I believe it's like the TI-83 calculator or the TI-82 that doesn't have this option. I know all the 84s have it. So if you have a TI-84, you're good. But if you have a TI-82 or TI-83, you may need to put this program into it in order to handle the calculation of our chi-square test statistic. I've also given you a process chart, like I always do every week, to kind of help you with your homework. Some kind of just a really terse summary of everything that we've gone over in our lessons today, so that you know how to handle the homework problems. So any questions from you guys tonight? Okay, looks like everybody is all right. For the final, can't have symbols on the note. the process notes, you can use the symbols, anything that you, I will take a quick look at the application assignment here in a minute. Yeah, I'll take a quick look at it to make sure that it's straightforward. I believe it is, but I'll make sure with you. Yeah, any of these symbols that you see in my process chart, you're allowed to use. The symbols that you cannot do, you can't say sigma equals population standard deviation, mu equals population mean, S equals sample standard deviation. Those are not allowed. You can't do that. But any of the symbols that you see in the process chart, you're more than welcome to use those in your notes. You just can't have a list of what the symbols, what they're called. We expect you to know that. You can write them down during the exam on your exam paper. Do not write them down on your formula sheet. Write them down on your exam paper. But yeah, if you're doing like a memory dump and you want to put this stuff on your exam, that's cool. I'll understand that's a memory dump. If you've got them on your formula sheet, then we've got some problems. So just don't write them on your formula sheet. So what do you mean by the formula for the critical value, Amanda? You could write the formula down, but you can't write the critical value for 95% is 1.96, for 90% is 1.645, and so on. You could write the formula down, but you can't have a little chart of what the critical values are for different levels of confidence. In other words, again, we expect you to find that on your calculator or look it up on your table. So I don't know if I answered your question or not. Did that work for you, Amanda? Okay, yeah. If you email me and give me some more details, that would be great. And by the way, for those of you, since these questions are coming up, I do this with all of my classes. If you get your formula sheet together early and you want to send me a picture of it or a scan of it, I will look it over and say yes or no. I won't tell you, I won't say, oh, you need to add this or add that. What I will look for is to say, yeah, everything on here is legal, or no, you've got some problems with this information, you need to take it off. Inverse norm, yep, you can put that on your formula sheet, absolutely. Because that shows up on your process charts. Anything on the process charts is good, good on your formula sheet. You won't have any trouble with anything I put on the process charts for each of these guided notes. So yeah, so if you're feeling a little uncomfortable about some of the stuff you have on your formula sheet, just send me a copy of it and I'll check through it and say, yep, you're good. Everything on here is fine. Or if there's anything suspicious, I'll say, oh, you need to take this off. It's not allowed to be on here. Any other questions before we look at the application here real quick for those of you who want to stay? I just want to make sure I didn't miss any questions in the chat box. Okay, I'll assume I've got all the questions. If not, just go ahead and pop it into the chat box. I'll keep an eye on that. So let's just see what we're up against for our application this week. The one I remember is pretty straightforward. I just want to make sure they haven't changed it. Okay. Here we are. All righty. So our application, yeah, statistics at work. Whoops, wrong one. That was from this week, right? I need to go to week 10. Boy, this semester's gone by quicker than I thought. I'm running a week behind here. Let's see, week 10. Oh, of course, it's going to be behind my thing here. Yeah, wrong week. I am just trying to get over here. Let me see. Just trying to make this a little smaller. here. Let me see if I can get my keypad up here. Sorry. Yeah, I know it's the one worth, let me see if I can get this to behave here. Here we go. So if I can just get it small enough. I've got these little boxes here and I just can't get them out of the way, it seems. So here's week 10, application, announcements. Okay, I know we have, boy, this is a real mystery. Group assignment. Maybe we don't have a week 10. Oh, here it is, a week 10 application assignment. I didn't see the button. I'm going to, if it's not there, I'll email it to all of you. Maybe I'm just not seeing it. Strange things start to happen after like 7 o'clock at night for me. Okay, here we go. Getting the scoop. All right. Let me grab it and pull it down. Okay, yeah, it looks like we've got, so yeah, this is a little different. It says the first one right here, let's talk about it for just a few minutes here. News of your analytic prowess has spread throughout the area. Naturally, when the coaching staff of your team's high school lacrosse team has a statistical question, they contact the best, that's you. The coaching staff wants to know if they can be 95% confident, which means alpha equals 0.05, that the average difference between the home team and their opponents is more than 2 points. Use the data below from 35 randomly chosen games to answer your question. So do we have paired data or independent data here on this one? Oh, thank you guys for helping me. It was apparently the fourth icon and I didn't see it. Yeah, we've got paired data. Awesome. So what you're going to have to do is you're going to have to put the first number in each box in L1. The second number in each box is going to go in L2. And then in L3, you're going to put L1 minus L2, what I showed you in that last problem. So first numbers in L1. So L1 would be 12, 8, 10, 14, 9, 7, 8, 5, 7, 8, and so on. And list 2 would have 6, 6, 4, 10, 8, 5, 2, 8, 2, 6, 4, 4, 6, 5, 4, and so on. And then L3 would be L1 minus L2. So that's what you're going to set up. Another thing that's a little different than what we did is here they actually want to know if it's more than 2 points. So your null hypothesis is going to be a little weird here. It's going to be U sub D is equal to 2. The alternative hypothesis, U sub D is more than 2. So you're not going to use zeros in this one because of the way the problem is set up. So I'm glad we looked at it. That's a little bit different from the normal setup. So let's see what else we've got going on over here. Just trying to get to my thing. Let me see. Okay, whoops. I would have never figured that out. Okay, glad we're looking at this. Yes. All right, good. So looking at the second one, just when you think it's going to be straightforward, they do something goofy in these assignments. Okay. Where is there we go. Okay. So looking at the second problem, yeah, this one about fireflies. So it looks like we have what kind of samples here? We have a sample of the number of fireflies that was taken before 9 p.m. and a sample of the number of fireflies that was taken after 9 p.m. So are these going to be, scroll back down, please, Stephanie. Oh, okay, sorry. I'm in the wrong place in the chat box. This is jumping around a bit. I'm not the only one that gets goofy after 7 o'clock at night. My computer does too. Good. Okay, yeah, these are independent samples. So it looks like we've got some data in L1, some data in L2. And this one, of course, is going to be that 2-samp t-test data option. Our first sample is in L1, our second sample is in L2, and so on for that one. So that's a pretty straightforward one. And then number 3, admission rates, that's a pretty straightforward 2-sample proportion. So that's going to be your option B on your calculator, the 2-prop z-test. So is what we're looking at here. And it looks like the dean has some questions for you that you have to be answering during the break. So the research director says she can't be sure. You notice in the footnotes of the presentation, the sample size, and that 46 of them continue. Yeah. Yeah, so it looks like we're going to be looking at the 2-sample, or the 2-sample proportion test, but it looks like you're just going to be answering some questions about it. I'm not sure you're going to be doing any calculations. You could do some calculations if you wanted, but it looks like you're going to be doing like a 95% confidence interval. Yeah, for this difference, interpret it to answer the dean's question. Yeah, so you're going to be doing the 2-prop z interval on that one. All right, and I think that's it. Yeah, that's going to be it. Yeah, so they're pretty straightforward with that little aberration in list 1. Yeah, in number 1. That's kind of a different way of stating paired samples. All right, good, good. So any more questions from you guys tonight before we call it quits? All right, looks like you guys are, well, thank you for hanging in there. And thank you for reminding me to look at the application, Eva. I appreciated it. Oh, you're welcome. Thanks for coming tonight. You guys have a great evening, what's left of it. And if you have any questions, remember just to email me.